Hey everyone, welcome to this really quick stereochemistry interlude as it relates to alkene addition reactions that we learned earlier this week. So far, when we're talking about these addition reactions to alkenes, we've talked a lot about how these reactions happen. And when we say that, we mean we've worked through the mechanisms together to help us better understand how these transformations take place. We've also talked about where these reactions happen, and by that I mean where specifically on a molecule, and that relates to the carbocation stability, which dictates at what position we're going to put our nucleophile at the end of the reaction. So that's kind of where we've been, but something that we haven't mentioned at all is sort of where in space these nucleophiles and electrophiles are interacting and attaching together. And so what do I mean by in space? What am I talking about there? Of course, we're doing this in a chemistry lab, in a flask. That's not so much what I mean. I'm talking about stereochemistry, the arrangement of groups in space. Now that we're aware of stereochemistry, it's going to show up everywhere. And so we need to pay attention to it in reactions where it's going to either get rid of some stereochemistry or maybe make some new stereochemistry. So as an example here, we have some alkene. This is the generic example that I've been giving for both of these reactions. This will be an addition of a HX type acid. We know that we're going to make a product that looks like this, where we've added that halogen to one side or the other of the alkene, whichever has the more stable carbocation. And that's fine, but this product doesn't tell us anything about the arrangement of that X that we just added in space. So this is not going to be specific enough. We want to instead opt for a more stereochemically specific answer to this type of reaction. So we're going to have that same carbon framework, but in one case, we're going to get the addition of our X as a wedge, and it is also possible that we get the addition of X as a dash. So why does this happen? Where does this come from? Let's take a look at it. The reason that we get both of these two products in what is actually an equal 50-50 mixture has to do with the geometry of our carbocation. So we looked at a picture like this previously that kind of shows our carbocation laid kind of flat in the plane of the page. And the other thing that I always love to draw in here is our p orbitals, right? Which look kind of like a big teardrop-shaped lobe both above and below the plane of our carbocation. So let's draw that in a different color. The plane of our carbocation is kind of like this, right? And it sort of goes behind that p orbital to show that we have some arrangement here in space. So we'll get rid of this little plain doodle there, just for some clarity. If we bring a nucleophile into this reaction, then we know we need to react with that p orbital in order to form a new bond. That's the orbital that is empty. So we have to kind of fill that in with electrons from our nucleophile, right? So if we were to do this, we kind of have two options. We have the top half of that p orbital, and we have the bottom half of that p orbital. And because they're equal in size, we have really no way of knowing which one that nucleophile is going to bump into first. So let's just say the nucleophile bumps into the top lobe of our p orbital. That's one possibility, but the other one, like I said, is pretty much equally possible as far as size goes. So let's draw that down here in a different color. But these are the two possible options of how this reaction could go. Note that you would not draw both of these on the same diagram if you were drawing a mechanism. This is just to illustrate a point about where things are arranged in space. So if we follow this blue path along the top here, that nucleophile is going to bond with the carbon from the top. So we're going to draw that in the plane coming from the top. Then here's our carbon, and everything else will be essentially where it was, just kind of maybe pointing downward a little bit to create a tetrahedral looking geometry. Okay, so there we go. That's the product that we would make, and we don't necessarily know what the R groups are, but let's think stereochemically for just a minute. Let's pretend that those R groups are numbered in order of their priority, and we'll call this nucleophile priority number 3. So if we've already assigned, based on our priority rules, which ones we think are highest priority, we can go from 1 through 2 and up to 3, noting that our hydrogen atom, or our lowest priority atom, is in the back, so we can go ahead and assign this directly. And if we follow that around, we will notice that that is going what would be the silly way around a clock. So we would assign this to be an S isomer of whatever this compound is that we've just made. Now let's check the red pathway on the bottom here and see what that makes us. So again, that nucleophile is coming into that bottom lobe and it's in the plane of the page. So we'll draw that kind of coming in from the bottom here. And then again, everything else is in the same place, just sort of maybe pointed down a little bit, again, for the sake of creating a tetrahedral looking geometry. Okay, so again, let's use our pretend priorities here to say that we have some R1. Oops, that doesn't really look like a 1 there, does it? It looks like an extension of that R. Let me fill that in, that's better. Now we could go from R1 through 2 to 3. And because of the position of where that nucleophile is has now changed, we actually get what looks like the right way to go around a clock, or the R isomer. So again, doesn't matter what these molecules are, but because we are able to have the addition of our nucleophile at either side of our carbocation, that means that we always have the possibility of creating an R isomer and an S isomer, which means that we would always create a pair of enantiomers. Now, the caveat to that statement is that if you were doing something which wouldn't create a chiral center anyway, then it's not going to create a chiral center anyway. But anytime a new chiral center would be created, you will create a pair of enantiomers. So what does this mean to you? When do you need to pay attention to it? So let's think about, when is this really happening? It's happening. It's always happening. It's just a totally random chance that we are going to get a 50-50 mixture all the time when we do a reaction like this with a carbocation. But it gets to be a little bit cumbersome to think about it all the time. So when do you, my lovely Chem 210 students, actually have to pay attention to it? That'll be only when I tell you to. So I have two example reactions that you might see in your homework or on an exam. So here's one. This is a predict the products question. I'll just move this up a little bit higher. There we go. So here's a predict the products question. And I'm asking you to do here the addition of water to this alkene. And if you just see this, that looks pretty much like what we've seen so far. And before, we weren't really talking that much about stereochemistry. So when you're here, you're writing in your answer, you would say, okay, I want to make the most stable carbocation, which would be at this position. And then after that, I know the water is going to attack and make an OH there. And that's correct, right? It's just not very clear and specific about stereochemistry. So that's fine. But if you were to instead encounter a problem that looks like this, where I say, hey, predict the product and be very specific with respect to stereochemistry, and I'll definitely put the words very specific in bold or italics or something, or all caps, to make you pay attention to the fact that I want you to tell me about the stereochemistry. I'm going to give you that hint, I'm going to give you that instruction if I want you to tell me. So if I were to give you this, predict the product's instructions, I would expect you to draw me the pair of enantiomers that are created in that reaction. So that's what you should be looking for as far as what is Grace actually asking me to do. If I'm not very specific, you don't have to be very specific. But if I ask you to be very specific, that means definitely draw me both stereoisomers. Okay, so with that, we'll wrap up this really quick video reminding ourselves about stereochemistry. If this felt a little bit shaky to you, or if you felt like you struggled with RNS and understanding relationships between different isomers in the previous unit, make sure you go back and look back into that, because it will come back in these reactions, it will come back in other reactions we're going to learn this unit, and even possibly in the last unit of the semester. So it's not going away for better or worse. And this is also a good time to mention that you just really need to keep practicing your mechanisms for the additions to alkenes. If you're feeling shaky on those at all, they will definitely be a part of our upcoming homeworks and exams. And if this is all feeling good, well, just get excited for polymers. They're coming very soon. And let me tell you, they're absolutely, definitely not a biased opinion here, the absolute best part of chemistry. So I'm really looking forward to sharing more about those with you soon. If you have any questions, feel free to leave a comment here, post in the discussion forum, send me an email, or stop by office hours. Take care.